Have you ever seen that strange purple glow coming from an indoor garden or a greenhouse at night and wondered, what's going on in there? Well, today we're going to trace that light all the way back to a brilliant 19th century biologist, some really clever bacteria, and what it all means for the future of farming. So let's just jump right into that central question, why purple? If you've ever passed an indoor farm, you've probably seen this super intense, kind of futuristic purple light. And I'll tell you, it's not for decoration. There is some seriously smart and surprisingly old science packed into that very specific color. Okay, so to really get why we even need these lights in the first place, we have to talk about the biggest headache for any serious plant grower: winter. I mean, think about it. From October all the way to March, there's just not enough good sunlight. The days are way too short, and the light that we do get is pretty weak. This can cause a condition called etiolation. It's where plants grow these long, pale, really flimsy shoots because they're desperately searching for light. And sure, you could use old-school lamps, but honestly, they're total energy hogs, and they often create way too much heat. But here's the cool part. The solution to this very modern problem actually began more than 150 years ago with a shockingly simple and elegant experiment. So, let's meet the guy who cracked the code, Theodor Wilhelm Engelmann. He was a German scientist who asked a really fundamental question. Do plants use all the colors of light the same way, or do they kind of have favorites? His method for finding the answer was, and I mean this, nothing short of genius. What he did was, he took a single strand of algae and used a prism to shine a tiny rainbow across it. But here's the brilliant move. He then added bacteria that absolutely love oxygen into the mix. And since photosynthesis creates oxygen as a byproduct, he knew the bacteria would naturally gather wherever the algae was working the hardest. These tiny bacteria basically became a living, breathing sensor. They pretty much ignored the green and yellow parts of the light, but they formed these dense little crowds right over the blue and the red sections of the rainbow. It was amazing. For the very first time, science could literally see which colors of light were the true fuel for photosynthesis. So Engelmann's experiment showed us what was happening, but it really took modern biology to explain the why. And it all comes down to the pigments actually inside the plant. This chart right here, this is basically the 20th century explanation for what Engelmann discovered back in the 1800s. It shows how much light is absorbed by chlorophyll, the green stuff that powers photosynthesis. And just look at those peaks. It's a perfect match to what the bacteria showed him. You see these huge spikes in absorption right in the blue-violet range, and then again in the orange-red range. But what's happening in the middle? A massive dip right in the green zone. Plants aren't using green light for energy at all. They're just reflecting it away. And that reflection, well, that's literally the reason plants look green to us. So the big question is, how does this old-school discovery hold up with today's technology? Well, a group of succulent fans in Germany decided to put it to the test with modern, super-efficient LED lights. This group, led by Schwentzer, took a whole bunch of cactus seedlings and set up an experiment. They grew some under pure blue light, some under pure red, and some under different mixes of the two. They wanted to see if giving plants only their favorite colors of light would actually make a real, visible difference. And wow, the results were fast. After only 2 weeks, you can already see these huge differences. Look at the seedling under pure red light. It's all pale and stretched out. But the one under pure blue? It's dark and compact. The experiment was definitely working. So let's jump ahead to 11 weeks in and really break down what these different light recipes did to the cacti. The results are pretty fascinating. The findings were crystal clear. Pure blue light gave them strong, dark, compact seedlings, exactly what you want for healthy, stout growth. On the other hand, pure red light caused that etiolation we talked about. The plants stretched out, they had very little color, basically they were stressed out. The mixed lights had different effects, but the main lesson was obvious. And this picture just illustrates it perfectly. You see, blue light basically sends a signal to the plant that says, hey, the sun is strong and direct, grow stout and strong. But red light, especially by itself, is more like the light you'd find filtered through the leaves of taller plants, which signals the seedling to stretch and reach for the sun, a process that can really weaken it. So what's the takeaway from all this? Well, when you combine that useful red light and that useful blue light, you get that unmistakable purple glow. It's not just a random color. It's a perfectly engineered diet of light, giving plants exactly what they crave and absolutely nothing they don't.
The bottom line is that modern LEDs let us be incredibly efficient. We don't have to waste a single watt of energy creating yellow or green light that the plants are just going to bounce back anyway. This saves a ton of electricity, it saves space, and it means we can grow healthy food just about anywhere, at any time of year.
And really, the results just speak for themselves. This isn't just for tiny little seedlings. Experimenters have grown plants like this Dorstania gigas from a single seed all the way up to a flowering adult, entirely under these LED lights. In fact, they've already used seeds from these plants to start a whole second generation, all growing under that same efficient purple glow. When you think about it, going from a 19th century algae experiment all the way to year-round vertical farms in the middle of a city, it's just a perfect example of how basic scientific curiosity can lead to really powerful practical solutions. It makes you wonder, right? If we can fine-tune something as fundamental as light, what other natural processes are we just on the verge of understanding and maybe optimizing?